Hey folks, welcome back. We're continuing on with taking a look at some of the building blocks here of hypothesis testing, and I want to talk about the level of significance alpha. Alpha was the thing that you were introduced to in Unit E. Remember when we were talking about confidence intervals, we said that we can't be 100% certain of our estimates unless we take a census. And usually we don't have access to the whole population, and so we take a sample, and that means that there's uncertainty. So we can only be, say, 99% certain, or 95% certain, or 90% certain. And of course, the width of the confidence interval is affected by that level of confidence. It's the same kind of thing here with hypothesis testing. So again, we can't be 100% certain when we are taking a sample. There's always uncertainty when you're dealing with a sample and not a full census. That means that we have to be okay with not being 100% sure, but maybe being 99% sure or 95% sure. If our level of confidence is 95%, then our level of significance is 5%. And that is the amount of acceptable error in our problem here. So alpha is the level of significance. And usual levels of significance are 5% or 1% if you want to be 99% confident, or 10% if you want to be 90% confident. Well, how do you decide that? How do you decide whether your alpha should be 5% or 10% or 1%? It has to do with this whole concept of what we call type 1 and type 2 errors. And so let's take a look at how that works. I'm going to go back to the court case here. And so here's a distribution. Think of this as being a distribution of sample means. And remember, the middle of this is going to be your hypothesized mu. Now, when we're talking about whether a person is innocent or not, this is implying some sort of numerical measure. And when you're talking about a court case, and it's a little different, of course. You're bringing in non-quantitative data and so on. But it's the same concept here. So I want you to think of the light blue distribution on the left as being our distribution of sample means, our X bars. It's like the 1.6 that we had in the cigarette example. Now, there's an alternative distribution, which in this particular case is that the person is guilty. And so there's two competing distributions here. Either the person really is innocent or the person really is guilty. So what we do is we bring in evidence, and what we do is we figure out, well, where does the X bar value fall on this hypothesized distribution of sample means according to HO? That's the innocence distribution. And if it falls way out here, in our particular case, we ended up with an X bar of 1.7. And again, I know it's hard to change that over into evidence about whether a person is guilty or not, but it's the same concept here. Anyways, if the 1.7 is much higher than the 1.6, or in this case, if we're saying that there's a lot of evidence which would tend to point towards the person's guilt, then we say the person is guilty based on the evidence here. The thing to note here, though, is that we could actually be making a mistake in doing that. This red part here is alpha. So this is the level of significance, and this is what we would refer to as being the rejection zone. So if our hypothesized value is, say, 1.6, going back to the cigarette example, and we end up with an X bar of 1.7, We standardize that, change it into a t, and figure out where does it fall on a t distribution. If it's in this upper 5%, then it's in the rejection zone, and we say that it's there's probably enough evidence here that they're not meeting the standard of 1.6, or in the case of innocence and guilt of a defendant, we would say there's enough evidence to say that the person is guilty. And so we conclude that the person is guilty if it falls in this red area, which is the rejection zone. It's more likely that the person is guilty. Problem is, we might be making an error there. So there's lots of cases, of course, where somebody is convicted because of circumstantial evidence, and it turns out later that the person actually was not guilty, and so ends up spending time in jail, or could even be executed. The problem is that there's the possibility that you actually let a criminal go free. And so what if the person really is guilty, but there isn't enough evidence to convict him or her? In other words, we end up with evidence that points us to this area right here. If that happens, even though the person really is guilty, it could be that there's just not enough evidence, and so we conclude that the person is not guilty. However, we could be making an error in doing that. We label these particular areas. This particular area here, let's do this as black. This particular area here is alpha. The probability of an error is equal to alpha. And this is what we call a type 1 error. So type 1 error happens when you reject HO when HO actually is true. In the court case, we conclude that the person is guilty based on the evidence, when in fact the person is not guilty. They're innocent. We've made an error. On the other hand, this area here is what we call beta. This is a type 2 error. A type 2 error, the probability is equal to beta, occurs when we do not reject HO, when HO is not true, when it's false. So in other words, the person really is guilty, but we don't have enough evidence. And so we conclude, therefore, that the person is not guilty and the person goes free. We've made an error and we've let a criminal out onto the street. So that is a competing error. Here's the thing, though, is if you take a look at the red area alpha, if we wanted to make that smaller, and so we wanted the area alpha to be not 5%, but say 1%, then we would move the line over here. But what happens to beta? Beta gets bigger. So these are competing errors. As one gets smaller, the other gets bigger, and there's costs associated with each one. Let me give you an example here. Consider the problem of our medical wizards trying to decide whether to market a new drug. This is actually a problem that I've had in my manual for years and years and years. But as I'm recording this, we're right in the middle of a COVID pandemic. And so we're taking a look now at some possible vaccines out there. Pfizer's got one that they say is 95% effective, and Moderna says that they have one which is 94.5% effective. This week, the Oxford vaccine came out in the news, and they said that it's 70%, but they figure with some fine-tuning they could make it 90% effective. And of course, they might have some others. So if you hear this particular video or watch this video much later, maybe even next year, of course, this will all be ancient history. But this is the way that they approach these things. The drug, or the vaccine in this particular case, is ineffective. That's the conservative statement, right? So remember way back here we said, I want to go back to this really important statement here, where I said, right there, HO always represents the traditional claim, the historical claim, the status quo. We could add in there the conservative claim. And so when we're talking about putting a vaccine out or a new drug, then we would say conservatively, because the thing hadn't existed before, that it doesn't work. You got to bring us lots of evidence that it actually works before we're going to risk putting it on the market. So over here then, the null hypothesis is always the drug doesn't work. Give us enough evidence to show that it does. So to test the hypothesis, the drug is administered to several patients, and the results are recorded. State some of the possible social and economic costs of a type 1 and a type 2 error. So a type 1 error is this red part up here. And so that is where we reject the null hypothesis. We reject HO when HO is true. In our case then, what we conclude here then is we conclude the new drug or vaccine is effective. When in fact, it is not. That would be a type 1 error. I want you to give some thought to some of the costs there. What are the costs associated with that? It means that the company is going to manufacture the drug. They're going to distribute it with the blessing of course, the government, if we're talking about, say, a vaccine for COVID. And it turns out that it doesn't work. What are the costs to it? Well, the costs here is that people are not cured or protected in the case of a vaccine. And so you end up with a bunch of people getting COVID and dying. For the company, it means that the company's reputation goes down. It means that there's possible people dying. The government reputation goes down. In terms of the company, whether it's, say, Pfizer or Moderna or whoever they decide to go with, it means that there's the research and development is reduced in favor of marketing going up. So what happens is marketing and distribution costs increase because they figure that they've found the drug. And so research and development doesn't necessarily stop, but it is reduced because they figure, well, we got the drug, right? And so they're not continuing on in terms of finding the right drug. The other thing too, of course, is that the competitors can get the jump. In other words, it turns out that the Pfizer drug doesn't work, but the Moderna drug does. We went with the Pfizer drug, and another country went with the Moderna drug, and there's problems in terms of people dying in our country, and of course the reputation of Pfizer goes down and Moderna goes up, and so we're going to go with the competitor next time, and all that kind of stuff can happen. So that's what we call a type 1 error. Now, type 2 error is the opposite. So a type 2 error is where we do not reject HO, when HO is actually false. So in this particular case then, this is the green area here, and the probability associated with that is beta. It's just a percentage here. And so in this particular case then, the type 2 error is that we don't reject HO. So we actually say that there's not enough evidence to reject HO in this particular area here, when in fact HO really is false and that this is the right distribution. So in this particular case, we would conclude, let's see, we do not reject HO. So we conclude the drug is ineffective when in fact it is effective. What are the costs associated with that one? Well, are you going to actually produce the drug? No, because your conclusion is that it doesn't work. So what happens, of course, is that you end up then with things like loss of potential revenue for the company, loss of people being helped, because you've got this drug that actually works, but there wasn't enough evidence to cause you to put it on the market. Okay, competitor gets the jump. Up here, I want to put down, back up here, you could have things like lawsuits, right? Your R&D, research and development, stays at a high level because you figure that you haven't got it yet, and so there's that loss here then of potential revenue because you're not marketing the thing. So you've got competing costs here. Now here's the thing. Which is the higher cost to the company? And it's probably going to be a type 1 error in this particular case then, is that you're not going to put the drug out unless you're really, really sure, because you don't want to have lawsuits. You don't want to have a loss of reputation. You don't want people dying on you because it's your fault. And so when we're talking about putting out a drug or a vaccine, they typically want to be about 99% certain that this thing actually works before they actually put it out here. The problem with that, though, is that even if you say 80% certain, they don't put it out even though people could be helped. And so there's a big social cost here, right? Loss of potential revenue, but also this one, a loss of people being helped. And that's why you end up with a lot of people saying, hey, just give me the drug. I will take the chance here. I don't want to get COVID and die. Or it could be something like a cancer drug, and you've got somebody who really is dying. And so they say, just give me the drug, right? But the company doesn't want to ruin its reputation by putting out a drug that doesn't work. and possibly have even worse side effects, such as in the case of, say, COVID or something like that. So that's the competing errors that we have here, is it's not just about having the smallest red area here, the alpha. We don't always go with being 99% certain because there's competing costs of making a type 2 error, which is the green part here. In most business problems, we tend to go with a 95% level of confidence, and so the alpha is 5%. But in medical cases, then they tend to go with a smaller alpha, about 1%, so they want to be 99% certain. What that means practically is when they say that they haven't proven that the drug is effective, then they might only be, say, 90% certain on that. And that's something to keep in mind. Let me give you another example here just before we end this, and that is that you'll often hear of studies where they talk about, say, things like health risks. I remember many years ago they were talking about, is there cancer, do people get cancer by living too close to those high tension power lines? And so they did some studies, and they found actually that in some studies that they said there's enough evidence to say that people who live too close, like within about 100 meters or something of these high tension power lines, have a greater chance of getting certain types of cancer. But then they did some other studies and they said, well, we couldn't reproduce the results. We didn't come up with the same conclusion here. The interesting thing about that is the second case there, they could have actually come up with it being 99 or 90% certain, but not 95 or 99%. So that's a really important thing to keep in mind with hypothesis testing, is typically you've got low alphas, levels of significance, which you want to minimize, especially when you're talking about things that have a high stake if you make a type 1 error. So that's where we're going to end this particular section here. Given that, how do you actually determine the costs associated with these kind of things here? If we were to go further in an advanced stats course, what we would do is we would talk about something called the power of the test, which is looking at the probabilities of various type 2 errors, so the betas, as the distribution shifts. And then you can do a cost-benefit analysis as to, well, what are the actual monetary costs or non-monetary costs as well, which is hard to quantify, but the costs associated then with certain levels of alpha and levels of beta. That's not something which we're going to do, and so in our particular cases, we will assume a level of alpha of 5% unless the problem gives us something different. So some problems will say an alpha of 1% or 10%, but if it doesn't say anything, then we will assume 95% level of confidence, which means a 5% alpha